So let's look at the Twitch streamer manager. Say hello Twitch. Okay, now let's go get the YouTube manager going as well. Okay, almost there. Sorry, a little slow today. Today is going to be annoying. Today we're reading documentation because I do not know USB well enough to know how hard of a challenge or easy it will be to do what I want. So, we're basically going to read documentation. So I got a few references. We can look for some more, but I'll talk you through it. Well, first off, what's the motivation behind this? We want to. Oh, actually, let me set up my Discord conversation over here real quick. Okay. I'm in stream chat. If you jump on, your voice will not be recorded on YouTube, FYI. But I will be able to hear your questions in real time. Okay, so motivation. I have the precursor FPGA. Actually, scroll down and look at the precursor right here. So we have the precursor FPGA, and it has a USB-C connection on the other side. I want to use this to do microblaze debug at one point. At first point. Second point, I want to use as a host to use JTAG FTD devices like the digital and JTAG plugin thing. So this device can program and cut other FPGAs. I need to understand USB to do that. So we're going to either design an HDL core for USB. I would like to do a VHDL version of it, or we'll try to leverage something else. So what I've seen so far is I found some two Verilog versions that are like 5 and 8 years old. I'm a little afraid to use those ones. And then I have two Python LiDX MyGen implementations we can look at. Let's see how well we can understand what needs to happen. Okay, so back to here. Currently, I don't see much of anyone. So this is going to be mostly me talking to myself. If you're listening to this later, hopefully I have a constant stream as I read boring documentation. But maybe we can come up with some information in the end. Oh, okay. I think I understand why. YouTube hates it when I change the entire image at once, because it's expecting a small differential. Okay, let's exit out of that. I guess they don't like me doing live and just going through screens. Okay, so not that, this one. So we have the official documentation, which, let's see, let's view full screen mode. Yay, let's see. Is there any waveform? Because there's a physical layer, a communication layer, I just wanna, we're just going to speed through this document to see if there's any useful information. But I mean, apparently we can go really slow. Like, what was this? You can go like down to a 1 kilohertz buzz clock. So maybe we'll try like a really slow one to start with. But yeah, let's see how far we get in a few minutes. Okay, okay. Let's get to like the nice data waveforms. Okay, that's something. But like, I want to understand how the digital bus works. We have two data lines, so we should be able to do everything off this differential data line. What else? Come on, give me something. Okay, here. Um, what's in NRZI encoding? A 1 is represented by no change in level. A 0 is represented by a change in level. So it don't really understand that. Okay. Um, okay. So we have this thing, this magical thing called NRZI. Apparently that's useful. And we can do sync patterns. Overall, from my background, I am not seeing any friendly information. Is there anything more friendly? We only have 650 pages. Protocol layer. This is what I want. Okay, I can deal with that. Got different packets, different information. Still going to have to learn how to translate it. I'll have to look at the other examples. But yeah, we'll figure that out. Hmm. Okay. YouTube's probably gonna hate that. Okay, we'll stop killing YouTube. YouTube doesn't like you when I just spam different screen changes. Okay, so let's go see. USB 2.0, we have D and D plus. Um, okay, let's see. Where is we want to look at USB A. No, that's not what we want. Cabling, power. Where is they not have the pin out? Category USB. Okay, the USB pin out Wikipedia. Guess it's just here. Um, where's the useful pinout features? Okay, moving forward. Pinout. Okay, so encoding. We're going to be doing NRZI encoding. We have to learn how to do this. But we should learn, I guess, how to do low speed, full speed, and high speed. eventually I want to be able to, what speed can we go? We can go up to this. This is oh no, nominal rate. We can do up to this 2x2. We can USB 420 GPS. This is how fast we can go with the FPGA. Not with the Arctic Ultra Scale Plus. So where's the pinout? They had a nice pinout chart somewhere. Where did that go? Okay. Oh, it's gonna be USB-C. Okay, yep. This is where I'm thinking. USB 2.0. So we're just doing the data in the V bus and they're connected. Do I have, where did I put it? Connected my headphones and now I can't hear myself. Oh well. Where did I put it? Okay. I pick up things all the time, bring them over and show, and get ready and get everything set up, and then I just forget it. I swear I moved it. You're going to have a fun second of not saying anything, but I'll be right back. Okay, I found it. And guess I'll put my headphones back on just for even though I can't hear myself over that. Those other connectors. Okay. Where are we going? Oh yeah. So let's see. How well can the camera see this? The camera is not focusing very well. So we have a simple USB 2 breakout for the, actually, is it USB 2? It has S bus. So what are the S buses for? Okay, yeah, it looks like we have a simple breakout. I guess we could do audio signaling. So basically USB 2-point breakout. Okay. So now non-return to zero. Inverted. Okay, let's read through this real quick because this is the type encoding USB 2.0 is going to be using. Non-return to zero inverted NZIR is a method of mapping a binary signal to a physical signal for transmitting over transmission medium. The two-level distinguishes data bits by the presence of the absence of a transition at a clock boundary. So input equals 1. Okay, no, NZRI right here. An example of NZRI encoding transition to 1. Okay, I still don't get that. Which bit corresponds to a transition varies in practice. The name is used for both. Or describe using conversion. The universal show bus program used the opposite convention. A logical zero is transmitted as a transaction, and a logical 1 is transmitted as no transaction. Okay, so 1 is a bit flip. That seems kind of weird. While bit stuffing is efficient, it results in a variable date rate because it takes slightly longer to send a long string of 1 bits than it does send a long bit of 0 bits. Okay, so let's if we go back here to the protocol, the go back to that NZRI example if we can find it real quick. I am curious. We can go through what, okay, we're getting closer. There we are. Right here. Data encoding. So Okay, so if there's a 1, that's no change. If there's a 0, that is a change in level. So here we go. So we have a 0 here, and that goes from our high J to K level. And another 0 takes it back up, 0 takes it down, 0 takes it up, down, up, down, up. So if it's all zeros, we just got up and down, all the way. And all ones means it stays steady. IC uses bit stuffing throughout the packet with the exception of internal bit stuff errors. Okay, where does it explain bit stuffing? Okay, let's understand bit stuffing. In order to ensure adequate signal transit, bit stuffing is employed by when sending a packet on USB, a 0 is inserted after every 6 consecutive ones in the data stream before the data is encoded. Zeros, 1. Zeros, 1. Okay. This forces a transition in the data stream. This gives the receiver logical a data transition at least once every 7-bit times to guarantee the data and clock lock. Bit stuffing is enabled beginning with the sync pattern. The data one that ends the sync pattern is counted as the first one in a sequence. Bit stuffing by the transmitter is always enforced except during high-end EOP, required by the bit stuffing service. Okay, high-speed signal uses bit stuffing throughout the packet with the exception of internal bit stuff errors. Okay, I think that's enough. So I think we got an idea of the NRZI pattern. Cool. Um, I want to check something real quick. Um, just going to check. Okay, here we go. Voice and output. Actually, I know how to check this. Okay, we're good. Okay. So we have two examples. We have the Bounty USB and the Luna. So let's take the next 40 minutes or 20 minutes each and try to go through these. So we have a full speed interface here. And if you remember, if we go back to USB, we can see the graph. Was it one of these? I think it was this one. Nope. Where's the graph? That graph. No, it's going to be USB. Where is NRZI? Okay, here we go. Signaling. So full speed. So Bounty US can do full speed, which is going to be the 12 megabits. So let's read through this. It requires a 48 megahertz clock and a 12 megahertz clock. That's easy. Using your project instantiate one of the CPU instances. Okay, this is in LIDEX, okay? MyGen LIDEX. The EPI instance is the most widely tested API. However, dummy can be used for designs without a CPU. So interesting. A dummy USB is a wishbone device with no CPU interface that emulates and acts as a wishbone bus. That's useful. Per endpoint FIFO interface requires a CPU to configure and manage the device. Maybe we can try to get this on a microblaze and play around with it. That may be useful. Or we can just do a dummy USB and see how it works. Right? I mean, yeah, we can try to get a dummy USB working. You can use built into the Linux distribution, communicate through the device, PID, wishbone tool. Or you can use the wishbone tool. And you can use the wish window to run a GTB server. Okay, yeah, we could probably use that. This might be interesting to try. We can test this out with the Linux machine. But yeah, so let's go into it real quick. We want to look at the USB transfer. Where was that? Yeah, USB. Right? Oh, there's a G there. Okay. So it's under SM. So we'll go SM. We're gonna look at USB transfer. I want to see, does this have the NRZI? This does not have NRZI. So we're gonna have to figure that out. So we bring in the IO bus. Okay, so the IO bus is running off the 48 megahertz clock, and we have these systems. And there's let's start with the IO bus. Okay, let's start at the very front of the system. So we go to IO. We're going to have a we're going to have the positive data pin, the negative data pin, and the pull-up pin. Pull-up pin, is there actually any documentation? Let's see, if we do a pull-up, right? Does this say anything about a pull-up? The pull-up reserve latency. Okay, yeah, so nothing too interesting about the pull-up there, but they use the pull-up, I think, to do like a host, or the host or the endpoint. We'll have to figure out how they divide between that. So we're going to mux it between the RX, the TX, and the RX paths. That's the muxing signal. If TX is enabled, if USB LSRX are okay, so interesting. And then we have the output, and the output enables. Receive lines. Where are the TX lines? Oh, here are the TX lines. Interesting. So it's using that line here to help tell what the RX signals are going to be. Okay, so we have that in this system. Okay, now let's go look at that USB transfer in the SM space. So in the transfer, we have the strobe. Where's the strobe going to? Where was this strobe defined? In the RX pipeline. Okay, we're just passing the RX strobe to the TX strobe. Okay, moving on. We may have to go to the RX pipeline to see what it looks like. Where is this defined? So it's gonna be an RX pipeline.py. Okay, let's see. ADC. Okay, anything useful? Data paths. Okay, so the data has already been serialized here. Try state. Signals. We have information. Okay, host device. We have the token data handshaking. This is the high level protocol. I want to get the low level pipe. I think we need to go to the pipeline to get. Okay, this is the high level information. We don't want to be there yet. So let's go to the receive core. And it looks like the pipeline was where we're going. Oh, I saw it. We have the NRZI. Let's go see in the pipeline where the NRZI is called. We have reset, probe, the USB signals, low speed support or not low speed support. Throw packet in, data clock recovery. Okay, we have clock recovery. I'm curious to how we are doing clock recovery. I say clock recovery a lot, but I don't understand exactly how it works. So I think that's where we're going to go next. Let's open that in a new tab. We'll look at that in a second. Speed. We have, okay, here's a decoder. We want to look at that next. That gives us the NZRI. NZRI. Those are the inputs. Okay, so we need to go see what the clock recovery core is. What is this clock recovery module doing? Inputs, we have the raw inputs. No need to synchronize. And we have outputs. Okay. Is this doing the NZRI stuff, or how does it calculating the D and the J? Line state recovery. This path doesn't use. Okay. Digital pair. Gotcha. We have a D pair. The receive path doesn't use a different receiver. Because of this, there's a chance that one of the differential pairs will appear to have changed the new state while the other is still in the old state. The following state machine detects transition and waits an extra sampling clock before decoding the state on the differential pair. Okay. The logical shift register, I assume. Okay, so we have the D pair. We have the logical shift register. Oh, okay. So if we're doing multiple samples, this is how we detect a going to a falling edge. How did this state it? Right, this is up here, right? K and the J. Oh, we want to go here. During a valid state, the value of the pair changes. Okay, here we go. Clock and data recovery. The DT for the line state recovery machine is used to align transit. The line state is sampled in the middle of the time. Okay. Bit phase 0, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Still trying to confuse how the K and the J. Four possible values. Okay, so we're just looking at what it could be. Oh, those are just the D pair. Looking for a differential in it. Okay. Not seeing this the best. We have a DK and a DJ, which I assume is the transitions we gotta send to the NZRI. So let's go look at NZRI. Indicates bus is currently in full speed J state, currently in full speed K state. So we have to assume this is the JK they're talking about for the NZRI encoding. Outputs, data decoded data bit from the USB bus is probably what we're going to care about. If false, what are you looking at? Okay. Um, Simple statement decodes a JK transaction as a 0 and no transaction as a 1. 0 is ignored. So let's follow the input, right? We have input IDJ. We stay in the 1 for the data. We have a DK, or if we have a DK, we go to 0. And if we have a DK, we go to 1. So a DK is switching it, a DJ is keeping it the same. That looks like what's happening. Oh, okay. So a DK transmits it to the data is a 0 in that situation, and then we stay here until we have a DK. And then once there's a DJ, we have a 0 bit and we transmit it there. Okay, sure. Man, this is more complicated than I assume. I need to, oh, this is gonna be hard to go through and play around. Okay, so we got the data. We have that for the decoder. So we have what was the output to the decoder? Outputs we have O data. So where is the NZRI O data? So this goes into packet detector, search the reset of the pipeline. Detect. So there we go. See what that one looks like. And we have the args bits stuff remover. So let's see what the beginning of a packet looks like. The args shifter version. Okay. And 12 domain. And then we just put in a FIFO. We have the data. And then we haven't even got to the protocol level yet. We are still in unlabeled. Full speed packets begin with the following sequence: KJ, KJ, K. This raw sequence corresponds to the following data. That's what we talked about. Plus IO condition signal with the J state. This translates to a series of ones since there are no transition. Given this information is easy to detect at the beginning of a packet by looking for 0001. The end of the packet is even easier to detect. The end of the packet is signaled with 2 S0s, SE0s, and 1 J. We can just look for the first S0 to detect the end of the packet. Okay, what was the SE0 here? Indicates the bucket is currently in SE0 state. Okay, that's from this guy. What is, we talked about what the SE0? It represents a SE0. I guess they're both 0. Both the pairs are 0. I guess so. Packet detection can occur in parallel with bit stuffing removal. Okay. So what we need to do is we need to go to WaveDrom. We need to go to the editor, and we're going to have to model these out. Ugh. We're going to need a DP, DN, actually. So this is going to be what, sys clock? We're going to have a yeah. Let me a slash in there. Do like a 0. Huh. Can we do like a J and a K? We'll do a J and a K. Let's just do 0 dot. Um, So we're gonna have to do like a DP, DN, and then we're gonna need to do a state. Right. Maybe like a 0, 1, 2, 3, 0, 1, 2, 3. Okay. 1, 2, 3, 2. Oh, those are just the colors. We just do 2, 2, 2s. 2 dot 2 dot dot 2. And we're gonna need to learn the DJ, the DK, the SEO 0, SEO 1. And this is going to be the company. Let's call it what do we call it? Just like what U state machine, like USB state machine. And then taking that input, we're gonna have the NRZI, and this is that gonna be a data one? I don't think it is. And it's just gonna be like a 1, 0. Like how the comma broke that. Right, and we're gonna want a 1, 0, 0, 0, 0, 0, 1, like something like that for a packet start. And protocol. What was that detect called? What did the book call it? Think pattern. Right, so we would do something like sync. Sync data bit pack question mark ends. Okay. And then we can do the line across, I guess, for the data packet end. Okay. Ugh. So I have a goal here now to now figure out how to do a few wave drums. Okay. Maybe we should probably move on to the next one. Okay, cool. So we dug into the input a little bit, the text and the packet. So let's try to find the same thing in Luna. Let's read about Luna real quick. Luna is a full toolkit. We have face dancer. It's software. Let's go to crowd supply Luna, right? We have this device here, still available for pre-order. This is the device they're mainly targeting. This is probably a great thing to get to learn about USB. I'm kind of regretting I didn't get it. If I say purchase options. Oh, not until December. Maybe later. We want to do this on our own system, so we'll figure it out. So yeah, this is doing the Luna. So analysis for low, full, high-speed USB for 2.0, and then creating your own full an experimental super speed. I want to get super speed working on this. So how about this? So this one's cooler, and I love this. So check out this issue right here. Hey, it'd be good to many users if we just move towards this and just retire this repository. I found this comment issue very funny. But let's moving forward. Provides a collection of MRF gateway alloys that allow you to create a USB device and gateway software combination of the two. MRF gateway. So we should learn how to generate the HDL for this. That would probably be a great step. But yeah, we might want to just start with this. So Luna, Great Scott Gadgets. Look for this guy real quick. Great Scott Gadgets. Yeah, found him. So yeah, I think it'd be a fun open source project to support. So I want to integrate this with Microblaze. So that's gonna be our first step, integrating this with Microblaze. Hmm. Do. Yeah, I guess that's gonna be our first hardware project. So let's go to Luna. Let's go look at the gateware. Let's go look at USB, I guess. We're gonna be doing what, USB 2. We have a transfer. Interfaces look like. Actually, no, what's the easiest thing? We just do NRZI, right? Where's the NRZI interface right here? Gateware 5. Where's the gateway? Okay, so gateware 5 receiver. We have a clock data recovery. That looks the same. That looks the same. Elaborate. That's literally the same. That's the exact same comment. So it looks like, okay, who added first? Who added first, right? You were last edited on December 11th, 2021. And you, my clock recovery friend, were last edited 20 days ago. Oh, so who is more up to date? That is the question. So we have a decoder now, NZR decoder. Very similar comments. A little bit different coding style. Good stuff remover. Okay, cool. So I say we take this one step at a time. That's a good question if we can actually do this little USB guy about the pull up. Let's go find out where the pull up's being defined. Um, let's see. All the locations of pull up here. Um, so this is where the pull up's being used. Where is it being assigned? It should be based on the term select. Pull up drive it based on the pull down controls. Okay, where is this term select? The term select is a signal. And okay, let's go find out term select. Okay. Okay, let's go up here. Wizards will connect the device full speed power pull up resistor. Is that what's happening? Is that we have a pull up resistor for full speed? Okay, tell me where this is being used in the system. I hate that you cannot use underscore. Okay, it's in the phi. Um, okay, let's pull this out. Look at all these different systems. Whoa, that we got someone in the chat. Okay, where is this term select? Okay, this is all we need. Term selects. There's one place. It's being driven high. Cool. That's the ports. I. Okay, so it looks like we're just driving high. We can do that on a Xilinx FPGA just fine. Okay, so it looks like we can do this on a Xilinx FPGA. We're going to have to learn the output on this. Yeah. Yeah, okay, that's good. So the Luna, you need to learn how to build it for a custom system. Okay. Let's go to read the docs real quick. How to setting up build. Let's get started here. Pip install poetry install copy of our local tools in a virtual environment. Testing the Apollo utility. Okay, I want to know how do you set this up? I don't want that. I want to be able to build it. What are the build commands? Okay. Self-made hardware bring up. Okay. Compile the bootloader. No. We want to git clone. I want to know how you build the hardware. How do you build the gateware? How do you build it? Is there no instructions on how to build the gateware? I find this lacking. Python scripts that construct and program gateware. Really, that's all. Okay, so let's go back to our. Where did the other one? I don't get GitHub, I guess. We go to these applets. interactive test. Where is the whole building process? I don't see it. Okay, let's go back here. Amaranth. Introduction. Let's see the tools. Lattice. Okay, we do support devices. Go fifth. Okay, so the next thing we want to do is let's go and check out Enjoy Digital Lidex. Lidex stock cores. What USB stuff? We have USB FIFO and USB OCHI. Let's go see what these cores are doing. PHY detection. That's looking at a FIFO that exists off board. I want a USB PHY. Adds data. Yeah, it looks like just the FIFO. What about this? Do we have anything here? Adds. Okay. Get the DPI. Okay. Instance. What's handling this? This seems so... Okay, yeah. Where is this USB stuff going into? This like a different interface? Okay, who is using this? I want to understand where this is being used. In this user code. This, what does this do? Okay, let's see. This is a PMOD. Vigilance. USB OHCI. What is this? Um, okay, let's do a PMOD. The USB UART PMOD. Is it this guy? Is it taking this to the next level? Support reference manual. Okay, that's not useful. Yeah, that's just a straight up UART, nothing useful there. So what are you actually supporting here? DPDM. It looks like it just shoves us into software, right? That is all that I'm seeing right now. We have these signals. We have oh, where is this? So final.lib. Okay, this is final. No, I did not mean that. Thank you for taking me seriously. So what do we have here? Nope, nope, still not useful. Let's go final HDL. Right. Okay, so we have a Scala version. What is this doing? We have a USB LFI. I think that's where we need to go. Let's go figure that out. Please. Thank you. Um, USB hub PHY. So I do not know Scala well enough. Um, okay, let's do one of our NRZI, right? Was that what it was called? NRZI, right? So no NRZI. So it's not enough phi. Block domain. That looks right. What do we have a decode? Coder. We have a J, one J, course J and K. Wow. Scala is crazy, man. Hmm. Okay, so we got a few different implementations. We got the Valenti USB. We have the Luna. Luna, I suspect, will get some fun, work going. So let's assume. Now, you need to figure out how to generate these. Um, let's see. Let's look at examples real quick. Oh yeah, here we go. The um, I don't I don't know how that. You just run these. You run though. The other thing, is there anything else in the docs besides what we have? Where? Okay, so I think we've exhausted our time today. So we got a few places. We have a Linux based system. We have a Spinal HDL based system. We have a AMRAT. What was it? We have a back and too far. Yeah, wherever the docs say it. An Amaranth HDL based project. No simple Verilog, no simple HDL. Nothing I can put into something and easily test, follow the convention. So, we're going to do an HDL one because I want to understand how it works. And what's the easiest one to understand? That's a good question. That's a good question. So, we're going to do WaveDrom stuff. Let's do some WaveDrom patterns and write some HDL to handle it. Then we're going to need to be able to snoop this line and respond appropriately to it. We didn't even talk about switching. We've been looking at receiving, didn't even talk about switching over to transmitting. Oh, hello, comments. Yep. Thanks for the comments. Sorry I didn't read them when I saw them. I read them earlier. Thanks for watching. We're going to have to figure out how to do this type of system. Um, Okay, so I think that's it for now. I'm gonna work on a quick WaveDrome thing and then call it a night. But I guess if you guys want to join me, we are going to do a quick system. We're going to reference what is the idle signal? We have a new follower on Twitch. Thank you for joining us. In Busy Mage 77. So yeah, let's do a quick homework assignment of getting this encoder to work. So we're gonna look at. So this is saying that when the P is high, we consider that of 1 when the 0 is high, and then we have an S0 and an S1. We talk about the idle state. Did you say idle? The J state. Is that the same thing as this? Okay, let's see if we can figure this out. Currently in full speed, K state currently full speed. Okay, no, we're gonna here. So this is the raw DP, the raw N on the incoming pair represents in the incoming pair represents SE1 in the incoming pair. You don't explain what these things mean. If I go here and we type in SE1, how much are not on the data port SE1 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 got a few more. Is there a lot of fun stuff? Okay, I think we hit everything. Let's see. Does it explain SE0? We have way more of these. Okay, right here. No function. This pull down the representative will cause both D and D to pull below the single low threshold for the host or hub report is not driven by hub. This creates on the downstream facing port. So SE0 is when they're both 0. Okay. Use a single end of packet, right? A single SOE state for 2 bit times followed by the driving the lines to the J state for 1 time. We described the J state well enough yet? And I don't know. The end of a packet. Portion of EOP. Okay, J state is where we're constantly at 1. Okay. So constantly at 1 is going to be high on the bus. And okay, so we're going to sample negative. We're going to sample on the positive edge. And we're going to say that we're going to have a 1 up top, which is going to signal an idle, and then a 0.00. And this is going to be opposite of that 0.0. And then it's going to be a 1. Right, we're going to call that a J state. Okay, back over here. So and when we're 0, we switch. Okay. Yeah. So DJ is when we have one high, and DK is when we have below. And the data, we're in DJ, we're receiving DJ, we're fine. But when we receive not DK, we exit and go to DK. But we're only transitioning. Make a transition as a 0 and no transition as a 1. A transition is a 0 and 1. Okay, where's our nice little sequence thing? So when we have a 0, which will be a so a DK give us a 0. If valid. And that's data. Yes, I'm not sure how their data is being following data. Where receiving a 0 increments the start counter. Okay, so a 0 is transitioning from a K to a J. That's all that matters. So and so we consider a DK, but I'm just trying to understand how they're decoding this of going. You zoom in a bit. Yeah, we can zoom in a bit. Trying to figure out why this. So this should be this is the positive end. This is a negative end. Why is this transitioning? Why is that a DJ? Bit phase. Line state. Okay. Oh, it's not that. It's just that when we have a 0, we go to the DK. We have a 1, we go to the DJ. And what does that mean here? So if we have a DJ, okay, I'm in state DJ, my output it means to be flip-flopping, and that doesn't make sense to me. What's the raw data coming at? The string of 0 causes the end of data to toggle each bit. Is that the encoding or decoding? So this question right here, this is encoding, not decoding. So we're doing decoding. We're doing the opposite process here, where we have a J state and a K state. So this is how the data is transmitted. If it's high, it's J. If it's low, it's K. Okay. So let's go back here. We can do this. We can do this. We're doing decoding. We're going to put this here. Actually, no, we're going to put this here. And we'll have another one, which we'll call data. And this is going to have to be like a bunch of 2's as well, with data of DJ or DK. Let's get rid of this. Okay, so let's figure this out. It's going to be toggling the raw line. So this is DJ when the 1 is high, and this is DK. And these are going to be translated to J and Ks and Js and Ks. Okay. In the NZR decoder, what happens to SE0? Is SE0 just passed along? We just pass SE0 forward and we don't transition. Or we just ignore it. Okay. So we want this sequence here. Okay. Going back to here. We want this sequence. Want this sequence. So how do we get to the JK? And what's the idle? What was the idle? The idling is going to be a bunch of J's. So let's do a bunch of J's. And J is basically high. So J is basically high. This is K. So yeah, I think we just need to do like this, right? It's gonna be K, J, K, J, K, J. Okay. And this is just going to be the opposite. 1, 0, 1, 0, 1, 0, 1, 1. Okay, okay. And then we're gonna have next data, bar data, and two, 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 two. Okay, here, and that, that, that. Okay, cool. We're going to do there. Another X. And what's say X there? X, 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 X. Now, and then what? We're gonna do a 0, 0 there, 0, 0, and no, dot. Two state of zeros, and back to the bus being J, and 1J. Okay, so DJ there, DJ, and a 1, 0. Let's hold it there, right? Let's DJ. I think the sync needs to start with a J, so we might need to move that one up further. No, it starts with a K. KJ, 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 KK. Okay, so the KJ, 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 KK. So that's all the sync. So let's go ahead and put a dot here and a dot, 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 dot. And we'll forget the bit pack. Right, and we'll do data. Data is going to be dot, dot, dot. But we want to put the bar there. Yeah. Doop. Okay. System Verilog, yeah, would be interesting. USB, probably USB state. Let's get the bar in these other locations. There. Bar. Bar. Click, click, click. Bar. Nope. Bar. Nope. Dot bar. Cool. This is gonna be data. XX, right? Oh, no, what's the data gonna start? It's gonna start high or low. What does the USB documentation say? Okay, we're gonna say idle is high. And when we hit a K, okay, so A1 is represented by no change in level. It's represented by a change in level. So change in level. Change in level. Why didn't it not change a level again here? Ah, that's weird. For the data stream, the high represents the J state and the a string of zeros causes. Okay, so that's data 0 1 1 0 1 0 1 0 0 0 1. Okay, so when there's a change, that's so when there's a change here, so right, so we have a change. That's when it's going to when we have a change in here. That's when we're going to have a 0. So there's a change. There's a change, a change, a change. What did this do? Is that just okay? That's just an X, I guess. There's a change. There's a change. There's a change, but the same. So it goes high, and then boom, and then boom, and we're just gonna say dot dot high high, and this one here. Yeah, we're just gonna do a dot high. No, not that one. That one. This one right here. We want to do X. Oh, Z. That's a cool one. X or dot 2, and we're gonna need to do a J at the end. J. And dot dot dot. Okay, cool. We have this. We should save that somewhere. I should probably make a repository. I have a FPGA Zealot thing. We'll have to add this to repository. Let me copy this and we'll put that in a repository so we can start doing this. And I gotta figure out how to do GitHub WaveDrom viewers. Oh no, guys, missed out. Okay, cool. We saved it. You guys got to see a Razer screen. Okay, so I believe this is correct. I will post it to Twitter. Let's actually okay, this is the one I want. Clicky. Let us export it as a SVG WaveDrom. Let us take this, put it here. I do this right. Really? Okay, we're going to save as a PGN. Remove attachment. SVGs are better, but apparently you hate that. Let's go like this. We're going to edit the message and slap this on the message. We're going to delete this message. Did I do this right? Question mark. It needs a background. Can't even see it. I guess you have to download it and look at it. Okay, cool. Yeah, so thank you for this journey. Let us figure out how to do data. Next. Let's be USB B underscore key. We'll say 12. Okay, cool. I'll save that second. Okay, thank you for joining me. Hopefully we figure out more of how USB works in the future.